What is one of the most beautiful things about winter? Snowflakes. In the real world, they're beautiful ice crystals that fall from the sky that display unique repeating patterns of symmetry, like the ones shown on the slide. While they may just seem like delicate patterns of ice, there's a lot more going on. Snowflakes are actually fractals, infinitely complex patterns that are self-similar across different scales, created by simply repeating a loop. One of the most special snowflake fractals in mathematics is the Koch Snowflake.
Hi everyone! Welcome to our Fractal project. I'm Neil and I'm here with Julia and Olivia to explore the Koch Snowflake's various properties. What is the Koch Snowflake? It is a fractal curve found and explained by Swedish mathematician Helge von Koch. Overall, it can be categorized as having infinite length and a finite area. How is the Koch line made? Like shown on the screen, it starts with a straight line which is divided into 3 equal parts, and an equilateral triangle is made in the middle. From that triangle, more triangles are made, branching off.
As seen in this graphic, the Koch curve is similar, in that it has substructure identical to the original structure. As we zoom in, the pattern repeats itself infinitely.
What does this look like in various iterations in the form of a snowflake? Here's a code written in processing language that we modified, and it allows us to see how the snowflake progresses from the 0th iteration. First, I start with a simple equilateral triangle, and in the user input here, I can type in the iteration that I want to view. I'll just jump directly to the first one by typing in 1. Here you can see that it follows the Koch line pattern, but all the sides are connected. The second and third iterations look like this, and you can see how the pattern continues, but it becomes smaller and smaller.
The first property that we will be exploring is sides. The formula to find the number of sides is s equals 3 times 4 to the n, where s is the number of sides and n is the nth iteration. Each side gains a new triangle in the next iteration. The 4 comes from the number of new segments made after every new iteration. For example, in the first iteration, it can be seen that each of the 3 original segments from the 0th iteration turns into 4 distinct but equivalent segments. That's where we get the 3 times 4. Using this equation with the 0th iteration starting at 3 sides, the first, second, and third iterations have 12, 48, and 192 sides respectively.
Next up, finding the length of each side. The formula for this is L equals x times 3 to the power of negative n, or x divided by 3 to the power of n, where L is the length of each side, x is the length of each side of the 0th iteration, and n is the number of iterations. This goes back to the pattern of the Koch line, where each line, or side in this case, is divided into 3 equal parts, and an equilateral triangle is drawn using the middle segment as a base. This means that this division happens n times, so the original length x is divided by 3 to the nth power times. Iterating this so that n is tending towards infinity results in the length of each side becoming smaller and smaller and infinitely closer to 0. The length of each side starting at the 0th iteration is x, and it is x divided by 3, x divided by 9, and x divided by 27, respectively for the first, second, and third iterations.
This leads to the second property, perimeter. The perimeter actually increases with no bounds as the number of iterations, n, tends towards infinity. To find the total perimeter, multiply the number of sides by the length of each side, which can be found through the equations from before. They're written again here below. Here's an example demonstrating the formula. Each side of the 0th iteration, the equilateral triangle, has a length of x. So the perimeter is 3x. In the first iteration, each of the original sides is divided into equal segments that are 1/3 x. Since there are 12 sides, this means that the total perimeter is 4x. And now for some FAQs.
The first FAQ is how is the area of each snowflake affected by each iteration? The area of each newer triangle can be found through the equation a is equal to a over 9 to the n, where n is the nth iteration and a is the area of the original triangle. Each triangle made from each iteration becomes smaller and smaller. This also leads to an interesting property. The total area of the Koch snowflake is finite and not infinite like the perimeter.
Using the 30, 60, 90 triangle, we can determine the height of the equilateral triangle, which is 1/2 s times square root of 3. Using the formula for finding the area of the triangle, which is 1/2 base times height, the equation for finding the area of this triangle is the square root of 3 times s squared divided by 4, where s is the length of each side. Next, to find the area of the first iteration, we can add the ears of the smaller triangles. In this case, s is divided by 3 in order to find the length of each side of the smaller triangle. The same area formula is applied, but because there are 3 new triangles colored in red, we must multiply by 3. The same thing is applied here for the green triangles. There are 12 of them, so we multiply by 12, and each of its sides is 1/9 of the original s.
This can be simplified by pulling out this common term of the equation. When we break it down more, we find that the limit of the area of the Koch snowflake is around 8/5 of its original area. Here is a quick time-lapse of the work to simplify the equation. This is demonstrated in the example shown on the screen, where s equals 1. Using the two equations on the screen, we can determine the areas. The area of the 0th iteration is around 0.433, and the area of the nth iteration is limited to 0.6928, confirming that it is limited to 1.6 or 8/5 of the original area. So what does this mean? The Koch snowflake shows that there can be figures with infinite perimeter but finite area.
Another FAQ is, what is the dimension of this fractal? To find the dimensions of the Koch line, we use the equation m to the power of d equals n, where m is the magnification factor, n is the number of self-similar pieces, and d is the dimension. In this case, there are 4 self-similar pieces created every iteration, and the magnification factor is 3, because the scale factor is 1/3. The formula rearranged is shown here, and we can find that the dimension is between 1 and 2, 1.262. This shows that the length between 2 points on the Koch curve is infinite, so it is more complex than a one-dimensional figure, but not detailed enough to be two-dimensional.
What happens if some of the parameters are changed? This can be modeled with our program.
What if we divide the Koch line by 4 instead of 3? Originally, we divide the line segment by 3 and create an equilateral triangle with that length. But what if, instead of dividing our line segment by 3, we divided it by 4, but kept the amount of line segments the same? We will maintain the steps such that at least one of the angles created in this triangle is going to be 60 degrees. First, line AE is divided into 4 equal parts, and line BC is constructed at the same length. CD is obviously not that length. We can find this by using the law of cosine. After some calculations, it comes out to the square root of 5/8. And now what about the angles? We use the law of sine to find that angle CDB is around 15.89 and the angle BCD is 104.11. Here in the code, the 3 is changed into the 4. The Koch line, which originally looks like this, turns into something that looks like this. And in a snowflake form, this pattern will show up kind of funky like this. Here's a GIF of the different iterations starting from 0 with the equilateral triangle.
What if we change the angle of CBD to 90 degrees? This code here controls the angle, and instead of pi by 3, let's change it to pi by 2. This gives us this funky shape, and you can see the iterations here in the GIF.
Are there any real-world applications? Yes. Coastlines are actually self-similar. It might be easier to visualize it like this. Here's some of the coastlines of familiar landmasses. Let's take a closer look at the coastlines of the UK. As we zoom in, we can see how the shape is sort of similar. Coastlines are similar because they share the same detail at different scales, one of the characteristics of fractals. They have a repetitive crashing of waves, rise and fall of water based on tides, seasonal storms, and even more, which all sculpt it over various durations of time, just like self-similar fractals like the Koch line. The coastline paradox was explored by Benoit Mandelbrot, who was curious about the length of Britain's coastlines. He noticed that small increments in measurements yielded longer length. For example, measuring with a yardstick or meter stick would result in a shorter length than using a 12-inch ruler. This signifies that coastlines have a dimension between 1 and 2. The coastline looks like a simple line, almost straight and one-dimensional when zoomed out. The closer you get, the more irregular the coastline looks, so the dimension is closer to 2. Look how the 5th iteration of the Koch Snowflake we can clearly see each segment. When we zoom out or iterate more, like in the 7th iteration, the distinct straight lines become less clear because you can't see the patterns of the iterations. If zoomed out even more, the patterns of the Koch line become even less visible and it can appear as just a simple line. We can apply the perimeter equation from earlier to find the length of coastlines. The closest integer of the snowflake is 29, which is plugged in as n, and it results in a perimeter of 12,599 kilometers, where the length of each original side x is 1 kilometer.
Let's do a quick Google search. It matches right up with our calculation.
Thanks for watching. Sources have been linked below.